Hello, this is Dr. Johnson. I am one of the AP Stats teachers here at Capel High School, and I want to welcome you to this lesson on comparing two means. You will need your calculator for this lesson. So, what type of factual problem are we looking at here? Well, suppose you want to compare the mean of some quantitative variable for individuals in population 1 and population 2, or the mean for individuals who receive treatment 1 and treatment 2. That's the type of fact problem that we are looking at. Because we have two populations or two treatments, you will have to define two parameters, regardless of whether you're calculating a confidence interval or a test statistic. Mu1 minus mu2 is the difference between the two means. If you are doing a test, if you're doing a t-test, then we expect you to write out the null and alternative hypotheses. The null hypothesis has a general form: mu1 minus mu2 is equal to some hypothesized value. And the most common hypothesis is that the two populations have the same mean, or that the treatments have the same effect. But it's reasonable to consider other situations. Suppose the hypothesis is that there's a 20-pound difference between the mean heights of the senior boys and the mean heights of the senior girls. Then the null would be the mean of the boys minus the mean of the girls is 20. And I've listed the alternative hypothesis. A two-tailed hypothesis always has a not equal sign. A one-tailed alternative hypothesis has a strictly less than or strictly greater than. Again, do not mix up the null and alternative hypotheses. You will not get credit. Then we have to check the conditions. Now, fortunately, the conditions are the same for both a confidence interval and a t-test. The first condition is that the data come from two independent random samples or from two groups in a randomized experiment. If you're dealing with two samples, in this unit, you have to explicitly state that these samples are independent. That's a new requirement for this chapter. The next condition, independent observations or 10% condition. When sampling without replacement, you need to check that both samples satisfy the 10% condition. And finally, you have to check the normal population or the large sample condition. To satisfy this condition, both population distributions are normal or both sample sizes are large, that is, greater than or equal to 30. If either the population distribution has an unknown shape or the sample size is less than 30, then we expect you to draw a graph of that sample data to assess the normality of the parent population from which it came. Now, in this case, when you draw your sample, you're going to look for strong skewness and outliers. If you see either strong skewness or outliers, then do not use the t procedure. If you don't see them, then you are okay to proceed with the t procedure. Now, in my opinion, plotting samples is a pretty weak check on the assumption of normality, especially if the sample size is really small, but this is the way we roll here in AP Stats. A comment here on notation. If you're talking about the standard deviation of the population of mean 1 minus mean 2, then you use sigma. If you're talking about the standard error of the sample data, then you're using S. Just a comment here about the sampling distribution. When the conditions are met and the population standard deviations are not known, the sampling distribution of the difference in sample means will be approximately normal, with a mean equal to the difference in the population means and the standard error of difference in means given by that equation right there. And now we come to the formula for the confidence interval. When the conditions are met, an approximate C% confidence interval for the difference in means is given by that formula right there. Now, you know everything. You know the X bars, you know the S's, and you know N. What about T? T is the critical value for the appropriate degrees of freedom. Now, if you're using the t procedure on the calculator, which I'll explain in a second, that will tell you the critical t, and that with the appropriate degrees of freedom. So the the calculator will give you the degrees of freedom that go with that particular t statistic. I also mentioned here an older technology that we used to use before calculators became so good. The smaller of the samples approach is a pre-technology workaround. Do not use that. We now have calculators that can do the work for us, so I expect you to use the calculators to get the degrees of freedom. Okay, when the conditions are met, the two-sample t statistic for the difference of means is given by this equation. So in the numerator, we have the difference between the sample means minus the difference between the, well, this will be the hypothesized value, and usually that's going to be 0. And below that, we have the standard error. And to determine probabilities, you can either let the calculator tell you the probability using the calculator's t procedure, or once you calculate the t statistic by hand, you can use the calculator's t cumulative density function to find the probability. Again, don't use the conservative approach. We now have calculators, so we're going to use them. That equation that's on the right-hand side is actually the equation for the degrees of freedom. So it's you know, the degrees of freedom isn't just a black box. It does come from a formula, but thankfully our calculators will calculate that automatically. We don't have to do that cumbersome calculation on our by hand. So let's do this problem right here. After buying many helium balloons only to see them deflate within a couple days, Aaron and Jenna decided to test whether helium-filled balloons deflate faster than air-filled balloons. To find out, they bought 60 balloons of the same type and randomly divided them into 2 piles of 30. Okay, so this looks like they're going to be doing an experiment. They've randomly divided the balloons into 2 piles of 30, filling the balloons in the first pile with helium and the balloons in the second pile with air. Then they measured the circumference of each balloon immediately after being filled and again 3 days later. The average decrease in circumference of the helium-filled balloons was 26.5 centimeters with that standard deviation, and the average decrease in the air-filled balloons was 2.1 centimeters with that standard deviation. So you can see that the helium balloons seem to decrease a lot more than the air-filled balloons. So what we're going to be doing in this problem here is determining whether that difference between 26.5 and 2.1 is statistically significant, or might it be just random error. So the question we're asked to do here is, do these data provide convincing evidence that helium-filled balloons deflate faster than air-filled balloons? So the fact that we're asking for convincing evidence tells me we're going to be doing a t-test, not a confidence interval. So we're going to do a t-test. That means we're going to have to write the null and alternative hypotheses. The question asks us whether we have convincing evidence that the helium-filled balloons deflate faster than air-filled balloons. So that tells me we're going to do a one-tailed test, So now we have to go to the identify part, and here we're going to identify 2 parameters because we have, the 2 different treatments. So mu h is going to be the mean decrease in circumference on the helium-filled balloons, and mu a will be the mean decrease in circumference of the air-filled balloons. The problem did not give us a significance level, so we will use the 5% significance level by default. And let's go back to the question. It asks us whether the helium-filled balloons deflate faster. So we want to find out if the helium-filled balloons the decrease is greater. So the alternative is mu h minus mu a is greater than 0. So that's the identify part. Now we have to check our conditions. This procedure is called a 2-sample t-test for difference of means. So I want you to write that out at the beginning of the condition section. We need to check the random condition. The data came from 2 groups in a randomized experiment. So we don't have 2 samples here. We just have, we're doing an experiment. So here's how I handle it. The data came from 2 groups in a randomized experiment. Specifically, the balloons were randomly assigned to the air or helium group. 10% condition, I've mentioned before, we do not do the 10% condition when we're doing experiments, so I just write out, not necessary because there was no sampling without replacement. Then we have to check the normal and large sample condition. We are not told the shape of the parent populations, but our sample sizes are 30, which meets our condition. So since both are greater than 30, we can safely use the t-distribution. We can proceed. Now, turn on your calculator. Here's where we're going to use our calculators to generate the t-statistic and the probability, the p-value. On your calculator, go to Module 2, the Statistics module. We're going to be doing a test, so hit F3. What type of test? We're going to do the t-test, so hit F2. And what type of t-test? It is a two-sample t-test because we have two samples. Now, in terms of calculator input, the first thing it's asking you, what type of alternative hypothesis do we have here? And we are doing a one-tailed test, and we want to find out whether mu1 is greater than mu2. So that's how I set my calculator input. Then you have to load up the mean of the first sample, standard deviation of the first sample, and the sample size of the first sample. And then do the same thing for the second sample. I'll give you a second here. When doing t-tests, we always have pooled off. That was they used to use pooled on before calculators because calculating the stuff by hand was so cumbersome, and pooling made it a little bit easier. But now that we have calculators, we have pooled off for t-tests. Always have pooled off for t-tests. So once you've loaded up this data, hit execute, and it's telling you this. My t-statistic is a whopping 39.46. Wow. That is telling me that the calculated t-statistic is 39.46 standard deviations above the mean. That is huge. And of course, with a calculated t-statistic that large, we would expect that the probability, the p-value, is very close to 0. My calculator tells me that the degrees of freedom is 51.4. It generated that number by using the equation that I showed you a few slides ago. If you want, I'll show you here in a second here. Go to my next slide. So in the calculate section, I want you to write out the t-statistic. This is the formula for the t-statistic. So I have the mean of my first sample minus the mean of my second sample, and then minus, and here's where I put my hypothesized value. My hypothesized value was 0. And I put that over my standard error. And I can, if I want, if I have time, I'll punch that equation out in my calculator. But if I don't have time, I'm just going to take the number that I got from my previous slide, that was 39.46, and put that down. So my t-statistic is 39.46. Just so I remember what I'm doing, I draw a t-distribution. I label 0. A t of 39.46 is way off the graph. So, and then I can write it just like this, using technology with the degrees of freedom that my calculator told me, 51.4. My p-value is approximately 0. If I want to write it as a complete probability expression, I can say the probability of getting a calculated t greater than or equal to 39.46 is approximately 0. Now, if I just calculated the t-statistic by hand, I would add this bottom line that you see here. See the bottom line that says TCDF? My lower bound is 39.46. My upper bound is some arbitrarily large number, like 1,000. Degrees of freedom was 51.4. I got that from my calculator, and hit execute, and that will tell me 0, essentially, too. So that I can put that optionally. So there's our answer. There's our probability, 0, basically. Now I have to interpret, and here's what I write. Because the p-value is approximately 0, and that is less than my significance level, 0.05, we reject the null hypothesis. And when you reject the null hypothesis, then you have convincing evidence or statistically significant evidence that the alternative is true. So we're going to have to write that in context. So I say there's convincing evidence that helium-filled balloons deflate faster than air-filled balloons. The difference that we saw in our samples is statistically significant. So that's our p-value. That's our interpretation right there. Here's a good question. Interpret the p-value that you got in part A in context. So this brings us back to a question that we would have answered in chapter 9, interpreting p-values. This is something that students always need practice on. So remember, when we interpret a p-value, it is conditional on the null hypothesis being true. And the p-value is the probability of getting the sample result that we got. So here's how I write it out. Assuming that the mean decrease in circumference is the same for the helium-filled and air-filled balloons, that is basically saying assume the null hypothesis is true, there is approximately 0 probability of getting a difference in samples, that is 26.5 minus 2.1, equal to 24.4 centimeters or more by chance alone. That is my interpretation of a p-value in this instance. Testing suggestions for this unit. All answers must include context and units if it's appropriate. When I say we want context, that means we reference back to the facts of the problem frequently. When you're checking the conditions, I want you to state the name of the test or procedure that you're using. Remember to check the conditions. It is not enough to just state the name of the condition or put a check mark next to it or say that it was met. You have to use the facts of the problem to support the fact that the condition has been met. Then write out the formula and show your work. Unexplained numbers will be ignored and will be ignored on the AP exam as well. So those are my testing suggestions. Thank you for listening to this presentation.